Hello, can everyone hear me? Okay. So the title of the talk is BackPackers. It means that we have a backbone of backers who are doing actual work so that everyone can enjoy an easy life. And this is joint work with Phúc Thái, Hong Sang, and Dr. Jonathan Kars from multiple institutes. So we all know that Bitcoin having some performance issues from transaction slow and also high latency. And we like to fix this. That's why we're on here today. So, first question we want to understand, if we have one chance to live our life again, how we would live it, right? So we want to see, we look at the networking layer and we say, let's learn from the issues that we have right now with Bitcoin and trying to make a better life next time. So we do a comprehensive simulation, large scale, network layer, TCP/IP, UDP, transmission protocol. We kind of figured out what are there in the network in transmission. So what we're looking at is that, okay, in Bitcoin, 98% bandwidth are unused. Okay, we ignore all the user, download, channels, and everything, okay? So it's very simple, but it got the message. Largely bandwidth are unused, right? And then 1.3 bandwidth used, what are they used for? 10% for transactions and 9.7% for block propagation. This is before Bitcoin Compact become available, okay? So Bitcoin Compact going to change this. But anyway, 80% is overhead. What are they? We look into it and we see, 80% overhead is what the great talk of Erlay pointed out earlier, the overhead of sending invite, get data, send. And who can imagine that invite can take 80% of the overhead, right? That's crazy. So if Erlay is one of very needed proposal to improve the efficiency of the bandwidth for the Bitcoin. So bandwidth of Bitcoin turned out to be what we define bandwidth utilization is that the fraction of blockchain data that actually become useful. And for Bitcoin, it's about 0.13%. Take the number with a grain of salt, but the point is that it is very, very, very low, right? So elaborate scaling proposal, and we can put them into layer 2 off-chain scaling, like Lightning Network, layer 1 consensus layer, like Bitcoin NZ and DAC-based protocol and sharding, and layer 0, which are far and few between, like Bitcoin Compact, Fibro, Falcon, blocks route. I would argue that we need more solutions over here, and this is one of the attempts trying to, to make network layer better. So after all the simulation of many protocols, and we figured out that there are two performance bottlenecks. The number one, transaction relay. We already saying earlier that every node needs to send invite messages to all the neighbors. So if we have more neighbors, it's more secure against Eclipse attack, but at the same time, you need to send more invite messages. And the overhead, the relative overhead, could mean the ratio between the data, useful data that you send and the other protocol can be very high. So let's say for egg, you got about 200% protocol. And for 32 transactions, it can go up to 800%, very high. So what does it mean for the performance? So what does it mean for the performance is this. So bandwidth utilization limits, saying that if you have a relative overhead RO, then the utilization cannot be larger than this. Which means that if the overhead is 800%, you don't hope to get more than 11% of the bandwidth utilizations, so that is a hard cap, right? So unless you fix the bandwidth, the transaction relay, don't expect for high performance blockchain. Any claim out there should be taken with a grain of salt. So another issue is that we have very inefficient way to schedule how data is transmitted in the network. So look at the data in the network activity here. You see 3 spikes. They correspond to, the time when the new blocks are announced in the network. Then the network traffic spikes up. But most of the time, they're quiet. So this is a very bad way to use traffic, right? We have to fix this. We want to have a kind of flat line for every time, making networking bandwidth more effective. And also, when we look into who do the hard work to transmit a node to the neighbor, then 87% of the nodes doesn't do anything, just receiving the data from the other nodes, and then 5% transmit most of the data, right? And then they transmit more than 5 blocks at a time. So there's an issue of somebody have a lot of work to do and somebody have nothing to do. We need to balancing the work in the network. And also sometimes the nodes, the source, the block producers in the network doesn't have enough bandwidth to relay the block. So we introduced BackPacker. BackPacker again is an idea that we want to have another life. What do? We want to approach theoretical limits. So in the same way, it's a physical limit from the previous talk of the PRISM proposal. So we follow a philosophy of data first, ordering later. So which means what? So when consensus, we mean that we agree on the order of the chain action. So we split it into two things: the agreement on the set of the chain action itself, and the agreement on the order of the chain actions. Okay. So this philosophy has been used implicitly in Bitcoin Compact in some of the DAC proposals, like Conflux or the previous talk PRISM, right? But we just need to push it into another level. So the design overview is very simple. We introduce a new node role called backers. The role of the backer is trying to reduce overhead in relaying chain actions by batching chain action from users. So user would not broadcast or relay the network, the whole network anymore. User would route the chain action to the packers. Packer would batch thousands of chain actions together in what we call a pseudo block before broadcasting them. Now, broadcasting a big block like 64 kilobyte would be give you a much lower overhead, like 3%, instead of like 800% overhead, like earlier we say. So backers would broadcast the pseudo to miners who would actually continue using the proof of work to finding the nonce, and miners would solve the puzzle on blocks as before, and then once they find the blocks, they don't include chain action, but they include the references to the pseudo block broadcasted earlier. That's why this is the order of chain action that we're talking about. And the order is very succinct. And then what we call the block broadcasted by miner meta block. So it should be like compact block, but it's the kind of compact block, but even more compact because now instead of references to chain action, it contains references to pseudo block. So it's about 2 to 4 kilobyte only. Okay, in case that I run out of time, here is the comparison of the backpacker and the other protocols that we do. So there are two tables here. We have 20 megabytes per second on the network, and here we have 100 megabits per second. So here the throughput, number of chain actions per second, where each chain action is 250 bytes, and then we have bandwidth utilization for the different protocol and the propagation time. So we're looking at here that most of the protocol, including Bitcoin, which you the one before Bitcoin Compact, and some of the other proposals, Bitcoin NZ, and Conflux, and PRISM, and BackPacker, then most of the protocols cannot achieve high bandwidth utilizations for the fact that they do not have an efficient chain action relay. So even for the top one, like Bitcoin Compact, actually perform quite well with 400 chain actions per second without doing anything. And then our BackPacker can do about 20 times higher, up to 7,000. And the bandwidth utilization is about 70% of the network. So it means that there's not much room to improve over here. You can improve at most 30% of the result. And again, if we increase the bandwidth to 100 megabits per second, then we can reach to 38,000 chain actions per second. And our propagation is also very small, 0.8 seconds comparing to the other proposal. Okay, so it's unbelievable. Let's say how we did it, right? Is it true, or let's see. So again, a BackPacker, again, the role of trying to gather and batching chain action before issue them into pseudo blocks and broadcast them every 5.5 seconds. So it means that smaller data packet broadcasted more regularly in the network, so that you don't have a spy up like this anymore. You have more like flat lie, kind of lie, so you make the network more effective that way. And then to handle multiple packers packing together, we're using a soft spatial sharding. So basically, is that chain action will be hashed to the closest packer based on their public key, and it's like a sort of like a solution similar to a distributed hash table. So we're going to skip this one due to time limit. And then when the miner files a nonce, the solution for the blocks, they're going to just include, point out the references to the ordered list of pseudo block broadcasted earlier, so that can create a very light blocks of 3 to 4 kilobytes before they can broadcast to the whole network. And then miner are going to verify. So one thing different is that we only verify the solution. We don't verify the chain action at the first. We just verify solution, and then if the nonce is valid, we forward it. And then after that, we linearize and verify the chain action later. So that's why we later going to see that this one going to have to improve the propagation time in the network. So overall, we propose also 2 other techniques to optimize the throughput. We provide what we call throughput optimal propagation scheme, in which we're trying to do every node in peer-to-peer network is a load balancing, so that we can achieve the optimal throughput in the network. And in terms of latency, we apply a sequences of techniques so that we can achieve the theoretical limits in the network. And security, we achieve the same security with underlying Bitcoin blockchain or any blockchain protocol. So, okay, so we need to talk about, we claim that we achieve near optimal throughput and near optimal latency. So what does it mean by that? So here, first, for the throughput of the network, we define a peer-to-peer network model in which every node is bounded by uploading bandwidth. The idea is if a node wants to participate in high-performance blockchain, they need to have high enough download speed. Otherwise, they cannot keep up with the mining. So every node is bounded by the upload bandwidth, and then they have latency among the link, right, which is limited by the light speed in the medium. So with this one, we have to see the limit on the throughput. We view blockchain as a peer-to-peer file synchronization system in which the block producers are the data source, and the other node just replicate the data. So by a theorem in 2006 by Kumar and Ross, the throughput is limited by the upload speed of the source and what we call the average upload speed of the node in the network, which means you cannot do better than average upload speed in the network, right? And here is the definition of the average. So this set us a network theoretical limit for this. Unfortunately, then this limit, it may not be realizable in nowadays network because they need to have a fully connected. To achieve that average bound, you need a fully connected network, which is not true cases for the Bitcoin. So we come up with new bounds that take on the topology of the network. Okay, first here we assume that we know the topology, but later we will say that we achieve optimality without knowing the optimality. So let's say if you have a graph Z that captures the topology of the network, then the throughput can be captured by this multi-commodity flow kind of thing. You just need to trust beyond this one, the vibrating constraint on the capacity of the nodes and load balancing, the flow, feasibility flow. The idea is that the throughput is feasible if and only if you have a multi-commodity flow among from the source node to all the nodes in the network. You just have to believe me on this one. So we're going to introduce first some idea on how Bitcoin propagation scheme is not effective and how we're going to fix it. So here, let's say here a source node S, right? S would send, invite for all the neighbors. And suddenly all the neighbors get data, want to get data from S. So S had to serve 1, 2, 3, 4, and 5 nodes, right? A better schedule would be first, let S send to D, and then S send to E. And then D send to A, D send to B, E send to C, and F. This is more balancing schedule. So Bitcoin have no such smart feature that we need to give Bitcoin that kind of thing. So the idea is that we don't send the get data to the neighbor who sent us the first invite. We're building a queue system, and we're using some optimization technique to control the queue in the most optimal way. So technically, we're using a virtual queue system to start the invitation from the node, and we're using a virtual queue on the edges on every link so that we can serve how much a request from a node to the other node. We call it the pressure from a node to the neighbor. And the idea of load balancing is that we're going to send requests to the neighbor with minimum pressure. So if this guy have an easy line, send him more requests. And we serve the request from the neighbor with the maximum pressure. So this guy is in need of more packets. We're going to send him more, right? So by using stochastic queuing theory, we're saying that by using a system, then as long as the throughput is 1 minus epsilon fraction of the optimal throughput, then the queue is stable, which means the queue is bounded. The length of the queue is bounded. So the optimality depending on the size of the queue, so it means you have more queue, more memory to store the data, the more optimality you have for the constant epsilon. Right? So with this one, we claim that the throughput of our system is near optimal under the assumption that the pseudo block contains a limited number of duplicate and conflict transaction, and then miner eventually incorporated most of the pseudo block into the blockchain. The other one is optimal propagation time. So optimal propagation time is very critical for the network security, and I mean for the security of the Bitcoin as well as confirmation time, because shorter confirmation time would make selfish mining harder. So and also we have a theorem we can say roughly that the confirmation time kind of like proportional to the propagation time. So if we want to minimize the confirmation time, we want to do is minimize the propagation time. So that's my argument. So what is the theoretical limit on the propagation time, right? So the previous talk, Prism already addressed the issue. The physical limit is the time need to send data from one node to the other node in the network. So here we follow the same link. Let's say we have a network like this one. Here the source node, then the propagation limit would be the radius, which means the maximum latency path from one node from the source to any node in the network, plus with the time to verify the transaction in the block. So you have to do it at least one for each node. So this is the limit, right? Actually, we can even ignore the time to transmit the block data itself. So it's kind of like, seems to be a very tough lower bound, very difficult to achieve, right? Let's see, can we achieve this one? So let's look at Bitcoin propagation here. Let's say we have a path from V0, V1 to Vj. What happened? What accumulated latency on this one, right? The latency on this one happened by first you had to using invite get send from one block from the source to the next one, and this is going to incur 3 times the latency on the link, right? And then also you need to have the time to transmit data from one node to the other, plus any delay if you have. So this is for every link you need to incur 3 times the latency on the link plus the transmission time. And here you need the time to verify the solution, time to verify the transaction after each of the half. And again, you have to do it again for the next half. So overall, the propagation time in Bitcoin is quite high, and the major component, you can see here for one half, but then you have to accumulate it for every half. So one thing you see is that the verification transaction happen all the time here. That's bad. We need to get rid of this, right? Also, transmission time for every block. We somehow want to get rid of that one. Now, in our latency optimal propagation scheme, what we did is we do it differently. First, we don't using invite get send for the meta block. Again, we don't send the block. We send what we call the meta block, which is references to the links of the list of the pseudo blocks we broadcasted earlier. And this one again is 2 or 4 kilobyte comparing to 2 megabyte block in Bitcoin. So this one is very small. And then we don't even send it using invite get send. We just send it directly to the other node. This way we save the route time trip through the invite get send. And also because this one is so small, so the time to send to this one will be very quickly. And because from one node we send to all the neighbors, which means that it automatically flooded the whole network. And then it automatically finds the shortest path from the source to all the nodes in the network. That helps us to achieve the first component in the latency, which is the radius, the maximum latency path from the source to any other nodes. And again, because we just verify the solution and then forward it directly, we don't incur the time to verify transaction at every hop. We only incur it at the very end. That's why the time we occur only one time of the verification of the transaction, plus a very small time to send the meta block, which is 2 to 4 kilobyte, plus the time to verify the solution, the nonce, which is very small. So overall, this reduces the latency, from at least about 3 to 5 times comparing to what we have in the Bitcoin. So experimental study, how do we comparing our protocol to the other? First, we're doing a large-scale simulation framework. We built this one with the goal of, there are many proposals out there. And then the question was, how can we know which one works better than the other? How can we know, which one, what would be the bottleneck in each of the protocols? And then is there a way to rapidly, implement to see the aspects of different protocols? So we build a large-scale simulation blockchain, including the consensus layer and the networking layer, with different kind of topology, latency, and network capacity. We had different access delay, packet loss rate, and everything. So the full-fledged network simulation for blockchain with very choice of topology and so on. So you can just plug in the protocol here and using a event-driven way to write. So let's say you just need to describe what happened if the protocol you receive a block. Let's say, what do you do? Then you just write a few lines of code and you'll be able to measure different statistics for the protocol. So in this one, we compare all of the protocol for the other, and we compare Bitcoin, which is original one before the Bitcoin compact, Bitcoin C, which is Bitcoin with the BIP 152, the Bitcoin compact proposal, the Bitcoin NZ, the Bitcoin conflict, which is a directed acyclic, a DAC-based protocol, and also we have Prism and BackPacker. So we deploy 1,000 nodes randomly across the worldwide, and we got the average bandwidth to be about 20 megabits per second. So we scale the latency so that the time to travel around the world would be 2 seconds. The block interval, because we aim for high performance blockchain, we shorten the block interval to 10 seconds instead of 10 minutes. And the block size is the same with 2 megabytes. So here is the measure we see earlier, that the throughput. So the key thing is that for throughput, we achieve much better due to the more efficient transaction relay. We route the transaction to the backer and then backer broadcast the transaction. And because of the larger block size, procedural block size, it incurs less overhead. And then also, because of optimal routing, the throughput approaching the capacity up to 72 of the bandwidth utilization. So it means that there's a little room for improvement over here. For propagation time, we get as much as 0.8 seconds for the block to travel around all the nodes in the world in our simulations. And so one of the questions is the role of the backers. I didn't have a lot of time to talk about. Then what happens if they are faulty or they die or malicious? And we showcase that even if they are a large fraction of them die, the performance is still stable. And even when all of them die, then the network goes back to the performance of the Bitcoin right now. So it's kind of robust to behavior of the backers. And for confirmation time, because we can actually having shorter confirmation time, shorter propagation time, then the confirmation time actually lower than all the other protocols, including Bitcoin NZ, Conflux, and Prism. So we can achieve confirmation time in 45 seconds, assuming adversary of 20%. We also have a full-fledged blockchain implemented. This one we call the Fractal project, invested by Blockchain, and we have a real blockchain running. A real world is not at ROSI that we show, and we only achieve about 3,000 to 4,000 with the current network. Because the limit now is not because of the network anymore, but because of the computational limit, the time to verify the smart contracts and so on. So we deploy about 20,000 nodes and across Asia and America on Amazon and Alibaba, and then we achieve a consistent protocol of 2,000 to 5,000. The public testnet is available, so you can go to the website and then try it for yourself. So in summary, we propose scalability, proposal called BackPacker. The main idea, three main ideas. One is transaction batching to reduce overhead. It reduces overhead from 800% to 3%. The earlier proposal, like early, reduced overhead to about 50%. So early is good, but we are better. But early is compatible to Bitcoin. Our proposal right now is we still probably have to introduce some of the opcode in order to make it compatible with Bitcoin. About security, is because we have a lower propagation time, then we have a lower fork rate, and we can do shorter block interval to achieve higher performance and overall. And our project combined BackPacker and proof stake protocol called Iching can actually achieve both of the sustainable security and scalability. And Thank you for the listening and welcome any questions. Thank you.
When you do your experiments and you measure like your statistics, do you have an adversarial section of your network, like the nodes that are adversarial?
No, we just assume, for this type of confirmation time, we just assume that there is 20% adversary who actually doing, who may actually, if that they perform some malicious behavior, what can they do? But we don't actually simulate the malicious behavior. Yeah, thank you.
So kind of related to that, you extracted the VB, the verification of the transaction. So it means that any transaction that is sent is propagated in a pseudo block,
Right.
even if it's valid or not, or is it validated by the packer?
Right, so biker would be the man in the middle. They have to propagate the, the valid chain assets. Their incentive design for this one is actually more complicated to this than this. And, but it's for the best interest of the biker to include only valid chain assets, because they need to deposit money, and there's some mechanism that if they do that, you need to pay fee for that. So it's not good for them to do that.
And that delay is also in here?
Yeah, this delay is also in here, yes. Thank you. Yeah, we're going to put the paper online soon. Yeah, thank you. Yeah.
Okay, so let's speak again.
Thank you.